So fluorine, when you look on page 159, no, that's not 159. Page 161, when you look at fluorine, it's going to have a 4 in its box. And that represents the electronegativity. Carbon is going to be 2.5. So that means if we share these two electrons at between fluorine and carbon at this point, those two are being shared, where are the electrons going to spend most of their time?
In carbon.
Closer to the 4. Because the 4 is like the big guys with the tug of war, and they're going to pull, and the rope is going to go their direction. Okay? Now, these electrons don't move in a sense where they're being pulled in a certain direction. But what that 4 means is that fluorine is the #1 person you'd want to have on your team in tug of war. If you had a choice, you had them all lined up. All right, who do you want to pick? You guys have ever done that at recess, right? You know, first one picked. Fluorine's always the first one picked here because it has the greatest electronegativity. What would be the second one that you would pick that would have the greatest, probably pull on electron if fluorine wasn't available? Which one? Bromine? No. Well, what we have to do, you have to be on page 161. I'll give you some time to get your book out and turn away to 161. So you can kind of see what numbers I'm talking about. Page 161. So fluorine is the #1 element that, you can look at this analogy too. If fluorine has to share, it's a kid, it would be an example of a kid that never wants to share equally. Mine. You guys never did that when you were little, right?
Yeah, sure.
Mine. Probably did that when you were little when somebody took your toy, came over to play with you or visiting, you'd say, no, mine, and take it, right? Fluorine is the one that will do that. Okay? Now, if you look at the next one, what would be the next one? Which one? Oxygen, 3.5. That's the next highest. Okay? And then you'd have nitrogen and chlorine look like they're tied. And you just kind of work your way back, kind of away from that corner. Okay? So these two, carbon and bromine, carbon's 2.5, bromine is 2.8. Why did I draw bromine bigger than fluorine? You know why? Because it's farther down the nucleus and we add extra shells on. So if I asked you, why is bromine bigger than fluorine, you would not say, because it's farther down the group, but what you would say, it has 2 additional shells that make it larger. That's what you would say. Okay, and everybody would understand that. Oh yeah, I can see that. Okay, but these are about equal share. Carbon and bromine, they're equal share. They're about equal strength. Okay, do you guys have, when you lift, on the board there's lifts, right? Your maxes and different things. You can kind of see about who's the same strength when it comes to certain lifts, right? And so you can also see which ones are not equal, which ones are way different. And that's kind of like fluorine and carbon. Here, these two are about equal. There's not a whole lot of difference between them. They share pretty equally. Okay? So, you guys already know what the group trend is, right? What's the group trend? For electronegativity. Look at your numbers. You can see.
It's when you go over
Group means going up and down. Going down a group. What is it? It increases. No. It decreases. Yes. Going down a group, it decreases. Right? All those numbers are getting smaller. If you go from left to right, Josh, if you look on there, and you're going from left to right, do the numbers get bigger going across the period, or they get smaller? They get bigger. So the period trend is to increase across the period, and then down a group, they will decrease. That would be the trend. Okay? So the group trend decreases. Why? Well, the reason larger atoms will have electrons located at a greater distance from the nucleus. If you want to say the size of the atom is larger, that's fine. Because it's larger, then the nucleus will not have as good of a attractive force because of the distance. It becomes greater and greater as you go down a group. So a lot of times if you say the reason would be that the size of the atom is larger, which creates greater distance between the electron and the nucleus. Larger distances between two attractive forces means that the attractive force will decrease. And that's the reason. Okay. And as you told me, the period trend is increasing. As you go from left to right, the general trend is to have a greater attractive force for those electrons that are being shared between two atoms. Okay? Any questions on that? I'll get the reason here for period trend. It's the opposite of the reason for the group trend. Instead of larger atoms, we know they get smaller. So we'd say smaller atoms will have electrons located at a shorter distance from the nucleus. Their shorter distance means there's greater attractive force for those electrons being shared. So fluorine, if you look at its size, it's about the smallest of all of them. And then if you look at some big ones with low electronegativities, it's because the atoms are large in size. Okay? All right, I'm going to go to the next slide. And I kind of changed up the wording on that. Instead of, I just made it a little bit shorter. Smaller atoms will have electrons closer to the nucleus. In your book, go ahead and turn over to the page that kind of shows what's happening of ionic radii, and that's page 159. Page 159. Okay, you have two different things happening. The red circle, when you look at the red circle, that represents the atom when it's charged, when it's an ion. The green circle is the size of the atom when it's not charged, it's neutral. So it's the exact same size as what we looked at under atomic radii. Okay, so can you tell me what area, what general area, what type of element the red circle is smaller than the green circle? Where on there, Austin, where on there, when you take a look at general area on that periodic table, is the red circle smaller than the green circle?
In like the middle?
Middle, yep. How about on the left? Okay, what are those called? What are those elements called? What do we call those elements that are in the middle and to the left? What general group? That can be anybody.
Well, aren't they the S's and D's?
Yep, they're S's and D's. Yep. Let's get a little bit more general, looking at the periodic table and how it's kind of where we have certain type of elements that have that are malleable.
Like alkali metals.
Yeah, let's get a little. So we need to include all of them. So it's metals, right? All the metals do that. What charges do they have? Look at all the charges of it. The small circle is smaller than the green circle. What are their charges? They're all positive. Okay? Just like you guys are every day when you come in here. You're always positive. Right? You're never negative. Never negative. Okay? Alright. So, they're all positive. Okay? We're going to take some notes here in a second to show you that. Go ahead and look at where on the periodic table you're at where the red circles are always bigger than the green circles. That's the non-metals, right, Lindsay. They are the non-metals. What are those charges?
Negative.
Negative. Okay? They're negative. Okay? So, those non-metals, they tend to gain electrons and become anions. And the metals tend to lose electrons and become cations. Cations is a positively charged ion. Okay? Does that make sense? All right. Good. And there's a reason for that we'll have. And we'll go ahead and let you guys look at the notes that you guys just explained to me. First of all, we're not going to define ionic radii, but a cation is a positively charged atom. And an anion definition is a negatively charged atom. And in parentheses, what I put down, the way it becomes a cation is if it loses electrons, kind of like our metals. An anion is an atom that gains electrons, and that's like our nonmetals. So nonmetals like to gain, cations like to lose. And they kind of pair up and will do that. Now, I probably could have put this next slide and wrote some things on here, but I didn't. And so if you want to, this next slide is not a whole lot going on with this slide, looking at information. But just like you told me, the cations are the ones that are metals, the anions are the ones that are nonmetals. The question I stated to you before showing you this slide would be, and you guys figured it out, is that metal area, when it forms a cation, those atoms get smaller. What happens to metal atoms' size when forming a cation? They all get smaller. The red circle is on that page, 159, is all smaller. And the reason why is because it loses a whole outer shell. And I'll show that in a drawing. If you guys want to see a drawing of that, it's really evident why it gets smaller. Because it loses that outer shell. Loses that outer shell. I'll let you write that, and then we'll do a couple drawings here to kind of show you that. Okay. So before I started working on this, we started with sodium. And sodium has, supposed to be Na. Sodium has 2 electrons in the first shell, and it has 8 electrons in the second shell, and in the third shell, it has 1 electron. So what's the charge of sodium? When you look on page 159 and find sodium, what's the charge of sodium? Positive 1. There's just a positive there. So to get a positive 1, we get rid of this one electron, and you can see that it gets smaller. The atom gets smaller. Okay? So that's sodium. If we would do magnesium that way,
So subtract the electron and then you get that.
yep,
This one.
it goes to the point where it has a full outer shell. So it loses an electron to get that full outer shell we'll find later. Here's magnesium. What's the charge of magnesium on the chart? +2. So for it to become a +2, and I should erase this beginning because it's not a +2 yet. So there's magnesium. So then when it loses these 2 electrons, it's like sodium did, and it loses a whole outer shell. And it becomes a +2.
Is it either going to be positive, like non-represented?
It could be, but if it loses, it tends to want to lose, Lindsay, it wants to lose to where it's this way every time. It's 8. 8 is the magic number.
On the outer shell. There's
On the outer shell, 8. On all of these metals, 8 is the magic number that they want to get to. Everybody likes to have the 8 in the outer shell.
So it's not just, it might not only use 1 or 2 every time, but there's a...
Right, I mean, even we could even take aluminum. And aluminum is the next one on that list, and it has 3 electrons out here. So what will it do? There's those 3. Now, you get to a point where it won't want to lose, it won't want to gain, and so what area on the periodic table will we have elements that will not lose anymore, but they'll gain?
That's the non-metals.
It's the non-metals. It's the non-metals. You keep working across, you get to the point where you got 7 electrons you'd have to lose versus gaining 1. It's going to gain the 1 to get 8. Eventually, it's going to work its way to like fluorine. And here's fluorine, and it has 7 electrons out here. Well, it's not going to lose all 7. So it's going to bring in 1 electron, and this becomes -1, and then the trend is for them to get larger, and I'll share you with why they get larger. Yeah.
So, like, is there ever like a break when they just start gaining instead of losing?
Yeah, it's your non-metals.
So that's when they just start.
Yeah, if you look at your circles, there's the break. It's right along the metalloids. That's the break. Yeah, they tend to. Usually, when you get to like 5 electrons,
Then they start.
they tend to do it. But it also depends upon where they're at on the periodic table. If they're down lower, they're going to continue to be like metals down lower. So there's kind of a break there between metals and non-metals. Okay. All right. The last set of notes, without giving you the problems to do, is the reason for the anion size getting larger. And what you're doing is you're adding additional electrons. Additional electrons repel without addition of any protons in the nucleus. That should be adding. Without adding any protons in the nucleus. So we're adding electrons, and then the protons are not being added, so there's not additional pull from the center. They're just adding all these same charges to the same area. Well, they got to get bigger. It's got to get bigger. we're not adding any more pull on those extra electrons. So they're going to get farther away. Okay, so at the beginning of class, I had some questions I was asking. I'll just put those on the board, and I'll leave them up there. And then after a certain period of time, I'll go ahead and go to the next one. And then when you get them all written down, you can put them in your notes. And you just have to decide based upon the trends of your different areas. You'll have to determine if it's smaller or larger in size depending upon what it's asking. Okay? All right. So those are the next two, 3 and 4. So tomorrow, you come in, we got a shortened period, Wednesday, 30 minutes. We'll get this out right away, and we'll go through these trends and see if you're getting them right or not. And if you're not, readjust your thinking on why that's wrong. Okay? You don't have to give reasons right now. Understanding the trends is the most important thing right now. And then the reasons you can look up later and make sure that you get those down, okay, for Friday. Okay, so today is Tuesday. By Friday, you'll have similar questions on a quiz that will cover this information.
And Friday's the last day of retake, right?
Friday's the last day of retake. And I sent those retake sheets out. There's not a lot to it. It'll probably take you 20 minutes to do. And I'll just look it over. Plus you have the test you can look over when you come and bring that sheet in. Okay? But yeah, Friday would be the last day. Okay? Gives you Tuesday, Wednesday, Thursday. Still got 4 days left.